So think in terms of the fluid flow, let's say in a river, okay? In a river or any other body of water, you can imagine a vector field that consists of, we'll call it capital V. Let's say it is rho times little v, where rho is the density of the liquid. Right? In other words, mass per unit volume. That's, of course, a scalar field, right? The density could vary from one point to another. And that, of course, is a vector field, right? The velocity could vary from one point to another in this river or whatever body of water we're talking about, right? The liquid could be moving faster at some positions than others. And also the direction of velocity could vary from one position to another. Right? So if we multiply the density times the velocity, the scalar field multiplied by a vector field, the result is, of course, a vector field. So again, that's what we've defined as capital V here. And let's think about the divergence theorem for a moment. And try to interpret the divergence theorem in terms of this, the fluid flow here. Right, so in the divergence theorem, we've got the divergence of V. I'm going to use this capital V as a vector field. So the divergence theorem says that the divergence of V integrated over d tau over a particular volume, V, with whatever appropriate limits I need to have to reflect that volume, is equal to V dotted into n hat d sigma integrated over the surface S and perhaps I should add a circle, right? The surface S is a closed surface forming the boundary of the volume V. Right, so let's think about what the divergence theorem means. Well, both sides of the equation in the divergence theorem are really ways of describing the net outflow of liquid from the volume V. And I'm sorry, I'm using V for three different things here, right? We got a little v, which is the velocity of our liquid, a capital V, which is the velocity times the density. Both of those are vectors. But then I'm using the volume V as a limit here to represent the volume that we're integrating over to. So I hope that's not too confusing. That volume is obviously not a vector. So anyway, again, both sides describe the outflow of liquid from this volume. And let's think about why that's true. Let's start with the right side. Right, so we've got a certain volume. Right, S is the surface of it. Remember, the n hat unit vector is a vector at right angles to the surface pointing outward. So let's assume for a minute that V, the vector V, was pointing this way at this portion of the boundary of that volume. Okay, so then V would be parallel to n, or more or less, n hat rather. So that would give you a positive result for this dot product. And if that were true everywhere over the surface, in other words, if V was directed out like this through the entire surface, then of course you would have a similar positive result for V dot n hat through the entire surface. When you integrate over it, basically you're looking at the component of V that is essentially flowing outward through that surface, right? And that is describing, again, if V is this vector field right here, that's describing the amount of fluid that is flowing out through that surface, okay? So, and you probably remember the term flux integral for an integral like this. Right? Sometimes we refer to this as the flux through the surface. It's just the amount of stuff that's flowing out through the surface. Now I said net outflow. What I really mean by net is, of course, the outflow minus the inflow. So if there's liquid flowing out through the surface, that would count as a positive flux. If there's liquid flowing inward through the surface, that would count as a negative flux. And of course, you can see that also by thinking, well, what if we had, inflow through the surface like this? So my vector field V would be kind of pointing inward like that. N hat would be, of course, pointing outward, normal to the surface. So V and N hat would be anti-parallel, or at least close to it, over that entire surface. That means the dot product would be negative. And so if we have inflow instead of outflow, in other words, the flux integral gives us a negative result. Now, of course, we can have outflow through some parts of the surface and inflow through other parts of the surface. Right? We could have, something like that, for example. But in the regions, the portions of the surface where we have outflow, we have a positive contribution to the flux integral. In the parts of the surface where we have inflow, we have a negative contribution to the flux integral. So again, the result of the integral is the outflow minus inflow, or in other words, the net outflow. Well, we can actually kind of also see that the left-hand side of the divergence theorem really reflects the same thing. And to see that, maybe let's think for a minute about some vector fields. Let me draw you some examples of some vector fields. Indicate what the divergence is. If we have a vector field whose vectors are represented by arrows like this, in other words, let's say a uniform vector field pointing from left to right everywhere, same magnitude everywhere. In other words, if this is a fluid flow, imagine this is a nice smooth fluid flow, right? The velocity is the same everywhere in the water. The divergence of such a vector field would be 0, right? On the other hand, what if we have something like this? What if the vectors making up the vector field are all pointing outwards from some point in the center here, for example? Well, the divergence is non-zero in this case. In fact, it is positive. In fact, the word divergence is actually pretty descriptive of what the divergence really is, right? These lines diverge from a particular point. And so the divergence of the vector field V is non-zero at that point. In fact, it's positive because the lines point outward from that point. Okay? So, it's hard to imagine something like this happening with fluid flow, maybe. But if there were fluid being created, perhaps, in the center here, right? It didn't exist and is being created out of nothing. Obviously, that's not physically possible. But if it were, it could be created here and then be flowing outward. That would, of course, give us a positive result for the divergence. And if we put some sort of surface, like maybe the surface of a sphere surrounding that point that the divergence, that the lines are diverging outward from, then clearly there would be a net outflow through that surface, right? This integral right here would be positive, but this integral here, right, is also a positive number. And similarly, if you had inflow, right? If your fluid was flowing inward like this and maybe being destroyed somehow, again, that's not physically possible, but if it were, right, it could disappear at the middle and more could keep flowing in. In this case, again, we'd have a non-zero divergence. In this case, the divergence is negative, right? Right, so if the lines diverge from this point, it's positive divergence. If they converge at this point, the divergence is negative. And again, this would correspond, if we put some sort of surface around this would correspond to a net inflow through the surface. In other words, the flux integral would be negative, but then so would this integral be negative. So I hope that it kind of, I think, makes sense. And I hope you can see that basically in the divergence theorem that both sides of the equation are really just two different ways of describing the net outflow of liquid from this region. Now, okay, so in other words, let's say that the divergence is the rate of net outflow per unit volume. So when we integrate it over volume, like we are on the left side of the Green's theorem, the per unit volume part goes away, and the result of that integral in the divergence theorem is just the rate of net outflow from the surface. Okay. Well, let's continue to think about a liquid. We'll get to the electrical case in a few minutes, but liquids are easy to visualize, I think, so let's kind of explore that analogy as far as we can get for a moment. So the divergence of V would be 0 unless there is some fluid. By the way, the word fluid means either a liquid or a gas. So I actually could be describing a gas with what I said too. It's maybe just easier to visualize it with a liquid. The divergence of V would be 0 unless one of two things is possible. Unless the fluid is either created or destroyed, that was the example I used here. I said imagine this fluid's being created somehow at the center and then flowing outward. Or the other reason the divergence could be 0 is, and let's say and or, right, because both things could be going on, the density of the fluid changes. Again, go back to this picture where the divergence is positive here at the center of this region. Again, this could happen because there's fluid being created here and it's moving outwards then. Or maybe no fluid's being created, but maybe the fluid is decreasing in density, right? The molecules are spreading further apart or whatever. That's going to push material outward, right, as that fluid expands. So that could also produce a non-zero divergence. So there's kind of two ways, either creation or destruction, I'm counting that as one, or changing the density of the fluid. Either of those or both together could lead to a non-zero divergence. So let's define some quantities here. The derivative of rho with respect to t, maybe I don't have to define it, it's obvious, I guess, from what I've said here. Rho is the density of the fluid, so this is the rate at which the density changes with time. And then let's also define, we'll call it the Greek letter psi. This is, let's say, the net mass created. Again, we're imagining creating fluid here. The net mass created per unit time per unit volume. Again, that's not physically possible for a liquid to just be created out of nothing like I described here, but imagine it were, because perhaps there are other vector fields for which an analogous thing can happen, and so we'd like to leave this mathematically pretty general, so we can treat those other cases also. Well, essentially what I've just said in words is that the divergence of this vector field V is equal to rho minus, or I'm sorry, psi minus d rho dt. Okay? Okay, again, if both these things on the right-hand side were 0, the divergence would be 0. But if the divergence isn't 0, it could be either because there's fluid being created, right? And fluid being created here would lead to an outflow, in other words, a positive contribution to the divergence. And then also the density could be changing. The reason I put a minus sign in front of that, let's think this through. If the density increases, right, molecules get packed more tightly together as time goes on, that's going to leave more room for more molecules to kind of flood in and take the place of the ones that got compressed. So in other words, that would be a negative divergence. Whereas if the density increases with time, the fluid expands, it's going to push outwards, so that would lead to a positive divergence. Right? So in other words, if the density increases with time, again, it's a negative divergence, so that's why we put the minus sign in front here. And if rho dt is positive, that leads to a negative contribution to the divergence.
So if it's positive is pushing out, negative is closing in.
Well, so if the density increases, right, in which case d rho dt is positive, that means it's going to push fluid outward, or I'm sorry, no. Density increases, right? It means the molecules squeeze closer together. That means more fluid comes in to take the place of the fluid that's been compressed, right, whose density has increased. So that would make the divergence negative. So in other words, a positive d rho dt leads to a negative contribution to the divergence, and that's why I put a minus sign right here. So anyway, if psi is equal to 0, in other words, if there is no mass being created. By the way, when I say net mass being created, that of course means the mass created minus the mass destroyed. Right? If mass can be created, you could imagine it could be destroyed as well. So again, that's of course what net means. So if psi is 0, that would mean that there's no fluid being created or destroyed. Then, of course, this term is gone from this equation, and we can add the d rho dt to both sides. So then this equation tells us the divergence of V plus d rho dt is equal to 0. And this is something called the continuity equation. And, of course, it describes fluid flow. Because in reality, for fluid flow, we can't just create fluid out of nowhere, right, or destroy it. So, so if that's what we're physically describing, this term really is 0. But it also describes the flow of current.
You mean electrical current? Or?
Yeah,
okay.
Electrical current.
Okay.
Okay? Which in many ways, of course, is analogous to the fluid flow, right? It's just the motion of, instead of mass, it's the motion of charge, right? And so for fluid flow, the capital V that appears here, and of course it needs an arrow over it, is rho times little v as described over there. In other words, the density of the fluid times the velocity. Right, so that's the thing whose divergence we have here. And of course, the rho that appears here is the density of that fluid. In other words, mass per unit volume. Okay, so for electrical current, let's find a page here right here. For electrical current, rho, instead of being mass per unit volume, will be a charge per unit volume. Or in other words, a charge density. Right? Whenever you hear the term something rather density, it basically means the whatever something rather is divided by volume. Right? Charge density is charge per unit volume. Sometimes you hear about number density. That's a number of particles per unit volume. Ordinary density, by that rule, should be called mass density, right? It's sort of understood that's what we mean when we just say density, though. So anyway, when we talk about the flow of current, instead of V, the usual symbol is J, which stands for current density. Actually, I'm just about to do something that I guess contradicts what I just told you. Remember I said whenever you hear anything density is that per unit volume. This is actually not a current per unit volume because in a way that doesn't make any sense. What it is a current per unit area. I guess you could say for something in which 3 dimensions is the appropriate number of dimensions, then the density would be something per unit volume. But we're in a 2-dimensional situation, it would be something per unit area rather than per unit volume. The idea of this, let's imagine you had something like a wire with a current flowing through it. Right? I is current. Right? This wire has a certain cross-sectional area, A. Right? That's the area of a cut through the wire, let's say. And so as the charge carriers are moving through this wire, right, they could be distributed uniformly throughout the cross-sectional area. They could be maybe all on the surface. There could be more of them in the interior and not so many moving on the surface. Right? So we could talk about a little patch of area, in fact, an infinitesimal area. And if this is a cross-sectional cut through this wire, we could imagine, you know, a little piece of that, a little infinitesimal area that's a portion of that whole cross-sectional cut, and talk about the amount of charge per unit time, per unit area flowing through that little piece. So that's what this current density really is. It's the charge per unit time flowing through per unit area. And in fact, we could write the total current as an integral basically a flux integral, right? Where we take the current density, J, which has a vector, right, pointing in the direction the charges are moving, dotted into n hat d sigma, where n hat as d sigma as usual, d sigma is a little infinitesimal piece of area, like this little one that I shaded right here, and n hat is a unit vector at right angles to that area. And so if we dot j into n hat, it looks like from this picture that they're probably parallel to each other, but you could imagine a situation where they weren't, if the area were tipped to the side or something like that. So anyway, if you dot j into n hat integrated over that area, you get the total current flowing through that wire. Okay? Anyway, there's a continuity equation like this for current flow. Okay, the divergence of the current density J plus d rho dt equals 0. If you have sort of nice smooth current flow, like we were sort of maybe envisioning in that wire right here, you could, within that wire, you could set up some volume of space, okay? And you could talk about the divergence of J. Now, if the current is flowing in through one side and it just keeps going and out through the other side of that volume, then of course you have 0 net, where did I write this? Net outflow, right? Because everything that's flowing out through the right side flowed in through the left side at some earlier time. Right? So the net outflow is 0 in that case, and the divergence is 0, but also d rho dt is 0, the density of charge carriers, right? The charge density is not changing either. But you could imagine a net inflow, which of course would give you a negative divergence, right? More flowing in than flowing out, as long as the density of charge carriers in this volume were somehow increasing, right? If they were piling up in there. Right, that would be a situation where d rho dt is positive, but the divergence of J is negative, but of course they still have to add to 0 as the continuity equation requires. Okay, so again, there's a version of this not just for fluid flow, but also for the flow of electric current.
Would it be like charging a battery, like as the current density keeps getting increasing?
Well, no, not really, because, I mean, when you're charging a battery, the battery is the battery charging is part of a whole electric circuit, and the current doesn't just sort of stop when it gets to the battery. Those charge carriers keep moving past the battery. What happens is that when they go through the battery, they deposit energy into the battery, and that's being used to recharge the battery. But you know, you can't in electric current. In fact, part of this, I guess you could say, is because the natural tendency of charges, okay, like charges, like let's say the flow of electrons in an electric circuit, they're all negatively charged, so they repel each other. That tends to prevent any changes in the density of the charge carriers, because if they start to pile up, there's a repulsive force between them that will spread them out again. So there are, you know, forces at work that tend to try to prevent that sort of piling up. And the result, of course, is that if this is 0, then of course the divergence has to be 0 too, which means the current has to keep going, basically. Okay. Also want to talk a little bit more about the curl of a vector field. And perhaps, again, this is best visualized by thinking about fluid flow. I actually use this example of a uniform vector field here, and I said its divergence is 0. Well, it turns out also if we have a uniform vector field like this, its curl is 0 also. So again, if you had a nice smooth flow of water in a river, right? Same velocity everywhere, same direction of motion everywhere. Both the curl and the divergence of that vector field would be 0. What would it mean for a curl to be non-zero?
Flows aren't perpendicular or orthogonal. The flow lines. Or?
Well, the lines describe the flow, so I'm not sure what it means for the flow to not.
Well, your flow. I don't know how to word that.
I think you probably have the right idea, but you're maybe just not saying it, real accurately. But look, here's the way of thinking about it.
Sleep is important.
Okay. If the curl of V is non-zero at a particular point in space, and again, think of this in the context of fluid flow, okay? What it means is that then if you put a little paddle wheel, right, an infinitesimal sized paddle wheel at that point in space, then it will turn. Okay? If I put a little paddle wheel, right, something with blades sticking out like that or something, right? There's a side view of it. In this fluid flow right here, it's not going to turn, right? And you can analyze why not mechanically. You could say, you know, the molecules hitting the bottom blade right there exert a certain torque on it, which would tend to make it turn that way. But for every molecule that hits down there, there's a molecule that hits up here on the top blade up there that exerts a torque on the paddle wheel that would make it turn that way, and those two torques cancel each other out. So there's zero net torque and the paddle wheel doesn't turn. So how could the paddle wheel turn? Well, certainly if the fluid flow is kind of circular like this, right? If we have something like a vortex where the fluid is spinning around like this, then if I set down a paddle wheel there, it is obviously going to turn in that direction. So that would be a case where the curl is non-zero. And you know, actually, if you think about in Cartesian coordinates, the expression for the curl for a moment, you can kind of even see why this would be true. Right? In Cartesian coordinates, the curl of v, the x component would be the derivative of v sub z with respect to y minus the derivative of v sub y with respect to z, and so on, right, for the other terms. In other words, we're saying, you know, let's imagine x and y coordinate system like that. So what we're saying here is that let's say the x component, right, there will be terms in here that involve the derivatives of v sub x with respect to y and with respect to z. The x component of the velocity of the fluid is going to depend on my y and z positions, right? The x component of the fluid flow, for example, here is not the same as what it is down here. So those two positions here and here are different y coordinates. So obviously v sub x depends on y. You can see that's going to give you a non-zero contribution to the curl. Okay? So, but swirly vortices like this are not the only way of getting a non-zero curl. We could also, for example, have fluid flow like this, where a longer line reflects a larger velocity, right? Bigger speed. So the direction of motion is the same everywhere, left to right, but the motion of the fluid is faster up here and slower down here. And if I put a little paddle wheel in, now there will be a bigger torque on the top blade than there will be on the bottom blade, and that paddle wheel will spin this way. So that's, again, non-zero torque, right? And therefore a non-zero curl for this vector field. And you can see in this case also that the x component of the velocity, which is the entire velocity in this case, it's all in the x direction, but clearly the magnitude of v sub x depends on y, and it's bigger up here than it is down here. So again, you can see from this kind of expression for the curl that that's going to give you a non-zero result for the curl. So again, you know, the name curl is well chosen. It has to do with the curliness or the swirliness, I guess you could say, of the vector field. Right? So here, anyway, so again, here's the rule, right? Just visualize that little paddle wheel. Set it down anywhere in space if you want to. If it spins, the curl at that point in space is non-zero. If it doesn't spin, the curl is zero. Okay. Let's jump ahead now and look at electricity and magnetism. We've already talked about it a little bit in the context of electric current and the continuity equation. But let's look at Maxwell's equations, because Maxwell's equations are really the fundamental equations of electricity and magnetism, and they deeply involve vector calculus. Okay, we can't write down Maxwell's equations without vector calculus. So there are actually two forms of Maxwell's equations. I guess I need to get some more of these markers to equations come in differential form and in integral form. The integral form of Maxwell's equations is the form that you're more familiar with. That's the form you saw when you took Physics 222, or its equivalent. Right? We're going to derive those in a minute, but I'm going to start with the differential form, which are usually thought of as being sort of more fundamental. But the reason we don't use them in Physics 222 is we can't assume people know what curls and divergences are yet at that point. They haven't had the math that they need to do that. So, here's the differential form. Okay, the first one of Maxwell's equations, which is Gauss's law, says that del dot D is 0. I'll define D here in a moment, but what I mean by rho, let me start making a list of, this isn't working very well. Let me try to write that. Let me start making a list over here of the symbols I'm using in these equations. Okay, so rho denotes the charge density. So rho is the charge density, or in other words, charge per unit volume. I'll define the vector fields here that I'm using in a moment, but this one is Gauss's law for magnetism. The third one says that the curl of E is of course an electric field, is minus dB dt. Okay, this is Faraday's law. And then the fourth one says that the curl of H, and again I will define all of these things in a moment, is equal to J plus the derivative of D with respect to time. And this is the Ampere-Maxwell law. So J here is the current density. Same in the way that we defined over there when we were talking about the continuity equation. So again, a current I would result from taking this current density and integrating it over, dotting it into an n hat unit vector, which is perpendicular to a surface, and then integrating over that surface, right, as the d sigma integrates. Right? So the current, in other words, is the flux of the current density. So anyway, E is the electric field, of course. And that's a vector field, right? It has particular magnitude and a direction at each point in space. So think about a vector sitting at any point in space. D is something called the electrical displacement field.
Is that a D in number 4? Equation number 4?
Right here? Yeah.
Okay. Partial of D.
Yep, partial derivative of D with respect to T. Okay, so D is something called the electric displacement field. And you may not have seen this before, but it is closely related to E. in fact, in a vacuum, D is equal to epsilon naught times E, where epsilon naught is a fundamental constant of nature called the electrical permittivity of the vacuum. Okay? In some other kind of material, other than a vacuum, the general expression for D is that it is equal to epsilon naught E plus another vector P, which is the polarization, which in a material describes things like the fact that molecules can have more positive charge on one end and more negative charge at the other end, and then those molecules can be lined up in certain ways, especially in the presence of an external electric field, to lead to a polarization, which is described by that vector. I don't want to get into this in detail, but let me just say in most materials, this polarization P is proportional to E, so it could be written as a constant times E, in which case that term and this term could be combined together to give D as being proportional to E, and we'll write the constant of proportionality as epsilon. And epsilon sort of is analogous in this equation to what the epsilon naught was up here. So in fact, epsilon naught is, again, the electric permittivity of the vacuum. Whereas epsilon without any subscript is the electrical permittivity of a material. Right? Whatever kind of material we are in. And so in most materials this is true, and the values of epsilon for certain kinds of materials, it's different for each material, right? And it's tabulated. You can look up values for different kinds of materials. But I don't want to get into details about this relationship. For those of you who are physics majors and are going to be taking more electricity and magnetism, you'll see this in your upper division E&M class. But anyway, so D and E are closely related. They basically, in most cases, differ by one being a constant times the other. And similarly, B and H are closely related. Okay? You see, there's a D here and a D here. There's an E there. You can also see B's here and here, and an H down here. Those are the only things I think I haven't defined yet at this point. H is technically called the magnetic field. Although you probably think of B as the magnetic field, but technically B is something called the magnetic induction field. Although, people are often a little bit sloppy about the terminology here because it's so common to just call B a magnetic field that many times people do that. What I would suggest is that if you really want to distinguish between the two, say B field or H field, right? Use the letter to distinguish which one you're talking about. But anyway, these two are closely related, just like the E field and the D field were. And the relationship is that H is equal to 1 over mu naught times B minus another vector called M. M is the so-called magnetization. Let me remind you, mu naught is the magnetic permeability of the vacuum. I'm leaving room for something else here I'm going to write in a moment. right? It's a fundamental constant, kind of analogous for magnetic situations to what epsilon naught was for electrical situations. This equation is very similar to this equation right here, and the magnetization is sort of analogous to the polarization. The magnetization describes what's going on, for example, in a permanent magnet, right? Where you've got a bunch of electron spins all oriented in the same direction, leading to a magnetization, right? Now, in a vacuum, where there are no electron spins to line up like you would have in a magnet, in a vacuum, H is just equal to 1 over mu naught times B. And in many materials, not all, but in many materials, basically anything but a ferromagnetic material, right? Like iron or whatever, we could write H as 1 over mu times B, kind of analogous to the vacuum equation, except that mu naught is replaced by mu, and mu is the magnetic permeability of whatever material we're talking about. Okay, so I've defined all the symbols in here, and so let's take those are the most general forms of Maxwell's equations possible that I have over there on the left. Let's write them specifically for the case of a vacuum. So again, we've got no material present here. Okay, so we're going to start to look a little more familiar at this point. Okay, for the first one, for Gauss's law, D is actually, in a vacuum, epsilon naught times E. So the and epsilon naught, of course, is a constant, can be pulled out in front of the divergence. And then we can divide both sides by epsilon naught. And so that will leave a divergence of E on the left-hand side. And we'll have rho over epsilon naught on the right-hand side. Okay? So the divergence of the electric field is related to the charge density, okay, according to Gauss's law. Second equation, we're going to leave as is. The divergence of the magnetic field is 0. Okay? The third one, I'm going to leave as is also. So the curl of E is equal to minus dB dt. All I'm doing basically here is I'm rewriting Maxwell's equations entirely in terms of E and B. I'm getting rid of the D and the H fields that we originally saw, okay? Because E and B are more familiar to you. Okay, so in the fourth one, the curl of H, well, in a vacuum, H is equal to 1 over mu naught times B. The 1 over mu naught could be pulled out in front of the curl, and then we could divide both sides by it. That would leave a curl of B on the left-hand side. And I just said we were going to divide by mu naught, so there's the first term on the right-hand side multiplied by mu naught. And in the second term, again, we've multiplied through by mu naught, so that will sit out in front. And then additionally, if I substitute for D, epsilon naught E, the expression in a vacuum, epsilon naught can be brought up in front of the time derivative since it's a constant. So we'll have, we've already got a mu naught, we'll have an epsilon naught also times a dE dt. Okay, so that's what Maxwell's equations look like now, written entirely in terms of the two fields that we're more familiar with, the E and the B field. Forget the D and the H field for now. I just, again, wanted to write them in the most general possible way to start with. Okay? Okay, so let's first of all talk about the first two and how they make sense. The first one has to do with the divergence of the electric field. And we say that's related to the charge density. So in other words, if there are no charges, right, if rho is equal to 0, then the divergence of E is 0. Right? But if there's, let's say we have a positive charge, right, a positive point charge. We know that it sets up electric field lines that point outward away from it like this. Right? We just talked a few moments ago about the fact that when we have electric field, or when we have field lines, whether the electric fields or some other vector field, diverging from a point like they do here from this charge, that means we have a divergence of that vector field that's non-zero. In fact, it's positive because the field lines are pointing out. They're diverging from that point. So in other words, a positive charge, a positive value of rho, gives a positive divergence for the electric field. Similarly, a negative charge, we know the field lines point inward towards a negative charge. Pointing inward, as we just talked about, means a negative divergence. So the divergence is negative if rho is negative. Right? Makes complete sense. What about the second one here? The divergence of B, the magnetic field, is 0. Well, there's no such thing as magnetic monopoles, right? Magnetic poles all come in pairs, right? You can't have a north pole without a south pole or vice versa. Right? If you could, those would be called magnetic monopoles. They do not seem to exist. Okay? Or another way of saying it is that magnetic field lines can't end. Right? Electric field lines can end, but they can only end on charges. Right? They can have their tails on a positive charge, they can have their tips on a negative charge, but they don't end, right? This one doesn't end here, it just keeps going up to infinity, but obviously I can't draw it going up to infinity, but it does keep going. Similarly, these ones don't just start here, but they're coming in from infinity. Right? The only way that electric field lines, in other words, can end is on charges. Right? Magnetic field lines can't end, period. Magnetic field lines either extend out to infinity or they make closed loops and close back on themselves. But they can't end on anything like charges or, again, magnetic monopoles. Magnetic monopoles existed. Presumably, this equation would look something like this one. It would say that the divergence of B is related to something like the density of magnetic monopoles, probably with a mu naught in there somewhere also. Okay, so the first two of Maxwell's equations kind of make sense in terms of what we've already talked about with divergences. Okay? Now let's look at some mathematical consequences of these. First of all, what about Gauss's law for magnetism? Equation number 2. Well, we talked last time about the fact that whenever we have a vector field whose divergence is 0, it can be written as the curl of a vector potential. Okay? So the fact that the divergence of B is 0 means that there is such a vector field, we'll call it A, it exists such that B is equal to the curl of A. And so A is the so-called vector potential. Okay, so this is not a topic you looked at in Physics 222, because again, you didn't have the vector calculus knowledge at that point. But for magnetic fields, there is something called a vector potential. A is the usual symbol for it, and B is equal to the curl of A. Okay? We know that such a thing must exist because of the fact that the divergence of B is 0. And as we said last time, whenever we have a vector field whose divergence is 0, we can always write that vector field as the curl of a vector potential. Okay? So there is such a thing as A. Now, let's take a look at the third one of Maxwell's equations, Faraday's law. Okay? So that one, if I rearrange it by adding dB dt to both sides, I can write the curl of E plus dB dt equals 0. Well, let's combine that with what I just said already up here from Gauss's law for magnetism, namely we know B can be written as the curl of A. So we can rewrite this as the curl of E plus the time derivative of the curl of A equals 0. I'm going to leave the curl of E as it is, but in the second term, right, the curl involves various kinds of derivatives with respect to spatial coordinates, x, y, and z, or r, theta, and phi, or whatever, depending on whatever coordinate system we're using. But in any case, they're all spatial derivatives. Out in front here, we've got a time derivative. So we're differentiating with respect to different things here and here. We can do those in any order, right? We can change the order of those derivatives. So in other words, I can bring the curl out in front and the time derivative inside. So I can write that term as the curl of dA dt. And then I've got curls in both of those terms, and the curl is a distributive kind of thing. So in other words, I can write that equation as the curl of the quantity E plus dA dt. Right? So now the curl of that quantity is 0. Well, another thing we talked about is that, remember that if we have any vector field whose curl is 0, that means that that vector field can be written as the gradient, or minus the gradient, of some scalar potential U. Okay? And remember, the reason for this is that there's a vector identity that says that the curl of a gradient is always 0, right? So if you were to substitute this in here, you'd have the curl of the gradient of U being 0. We know that's always true. And in fact, we use a similar argument up here, right? B is the curl of A, so if you were to substitute that for B in here, you'd have that the divergence of the curl is 0. And again, there's a vector identity that says that that's always true. So anyway, the fact, though, back to this one, the fact that this is true tells us, since the curl of this quantity in parentheses here is 0, it means that E plus the partial derivative of A with respect to t can be written as minus the gradient of a scalar potential. Which I hope will not be too confusing if I call it V, because that's kind of the usual symbol for it. The only other place I think I've used V for the moment is right here, and this was just a generic statement about any vector field V. Okay? So V here is a scalar potential. Now, if there is no magnetic field, in other words, if B is 0, then A is 0 as well. Or at least A being 0 is one of the choices we can make for A. I think we talked last time, in our very last example that we did, about the fact that if you know vector potential exists for a certain vector field, because again the divergence of that vector field is 0, we talked about how to find this vector potential, and I showed you an example, and I said there's actually an infinite number of choices for it, but that usually all we care about is finding one. Well, again, A is 0 is not the only possible choice. All right, you could imagine some non-zero A, but whose curl is still 0, so it would still tell you B is 0. So in other words, I'm not saying B is 0 implies A equals 0 as a mathematical statement. Because again, you could certainly have non-zero A's whose curl was 0, right? So that would give you a B of 0. But certainly A is 0 is one of the possible choices for a vector potential in the case that B is 0, and it's the sort of the most logical and sensible choice. So let's make that choice, and let's say A is 0. Well, then of course dA dt is 0. And then this statement is just that E is minus the gradient of V. And this is, of course, our usual electrical potential. Right? When you were back in Physics 222, you learned that the electric field can be written as minus the gradient of the potential, right? And this is that same equation. And I guess perhaps we didn't say that in Physics 222, or maybe we should have and didn't. But that was under the assumption that we were not dealing with anything magnetic going on, right? Magnetism was something we talked about later. Okay, so we see that there are these two potentials, a vector potential and a scalar potential. Right? The vector potential goes with magnetic fields. The scalar potential, at least in the case where there's no magnetic field, kind of goes with the electric field. The electric field is minus the gradient of it. If there is something magnetic going on, then this equation substitutes for that one down there. Anyway, when I first wrote down Maxwell's equations, actually we're going to do a break, weren't we? Maybe this is a good time to do our 5-minute break. Well, we'll come back. I'll show you how to get from the differential form of Maxwell's equations, these ones here, to the integral form that you've seen before and are more familiar. So anyway, I told you we were going to take Maxwell's equations, and we're going to use the versions that apply in a vacuum right here. I don't want to worry about D and H fields. We're going to take the differential form of Maxwell's equations, which are these equations right here, and derive the integral form of Maxwell's equations from them. Those are the forms of Maxwell's equations that you have seen in the past, and so they will look a little more familiar to you. Okay? And then if we have time, we'll finish up by doing an example or two of those. Okay? So again, let's think about a volume tau that is bounded by a closed surface S. And let's take the first one of Maxwell's equations, Gauss's law, and integrate it over that volume, tau. Okay, so on the left-hand side, we have the divergence of E. We're integrating over the volume d tau. And on the right-hand side, we've got rho over epsilon naught, which we're also integrating over this volume tau. Well, the left-hand side here looks like the left-hand side of the divergence theorem. Right? The divergence theorem tells us whenever we have divergence of a vector field, E in this case, integrated over some volume, that this integral is equal to the integral of E dotted into n hat d sigma and integrated over the surface S, closed surface, that forms the boundary of this value, or this volume tau. So by the divergence theorem, we could replace this integral by this integral. And on the right-hand side, of course, the epsilon naught, the 1 over epsilon naught, can be pulled out in front. Rho, remember, is a charge density or a charge per unit volume. So when we integrate it over the entire volume, with whatever limits here reflect that volume, we're just going to get the total charge enclosed inside of that volume. So Q with the subscript E and C to stand for the charge enclosed inside our volume tau, or V, or whatever word you want to use for it. So anyway, the result then is that on the left side we've got the integral of E dotted into n hat d sigma, or dA, some books will write it instead, and that is equal to the enclosed charge divided by epsilon naught. So this is the familiar integral form of Gauss's law. Right? It says that if we take the flux of the electric field through the closed surface that forms the boundary to some volume, this is of course normally called a Gaussian surface when we use it in connection with Gauss's law, and the result is equal to 1 over epsilon naught times the total charge enclosed inside of our Gaussian surface. Okay? So that's, again, the integral form of Gauss's law. So you can see the differential form that we started with and the integral form are related by the divergence theorem, basically. Okay? Do a similar thing for the second one of Maxwell's equations. So again, we're going to integrate equation number 2 over some volume tau. Alright, so on the second one of Maxwell's equations, we have the divergence of B, so we're going to take that and integrate it over this volume tau. Well, the right-hand side was 0, and it's still 0 when we integrate it over some volume. Right? Integrate to 0, so the result is still 0. Well, then, again, let's use the divergence theorem. Right, the divergence theorem says that this integral here on the left-hand side can be replaced by the integral of B dot n hat d sigma integrated over the closed surface S that forms the boundary of tau. And the right-hand side, of course, will still be 0. So again, this is the integral form of Gauss's law for magnetism. Okay, so for the first two of Maxwell's equations, the differential form is related to the integral form. In fact, you know what I'm going to do over here? On this rightmost board here, because hopefully I won't get there for a while and I'm tempted to erase it. And if I start to erase it, stop me, okay? Because I want to leave these up here. But I'm going to put our summary of Maxwell's equations. So I'm going to write both the differential form and the integral form. Okay. Okay, so the first one, or Gauss's law, differential form tells us the divergence of E is equal to the charge density over epsilon naught, and the integral form tells us that the integral of E dot n hat d sigma integrated over any closed surface S, Gaussian surface, is the enclosed charge inside that surface divided by epsilon naught. Okay, the second one of Maxwell's equations, the differential form tells us the divergence of B is 0, and the integral form tells us the integral of B dot n hat d sigma over any closed surface S is 0. Okay, so you might be guessing, right, since the first two involve the divergence and the second two involve curls, and for the first two we use the divergence theorem to rewrite them, you might guess that for the second two we're going to use Stokes' theorem to rewrite them, right, and you would be correct. So let's now, for the third one, consider an open surface, not a closed surface. Remember Stokes' theorem we normally use for an open surface. You can use it for a closed surface. It's not untrue. It's just kind of trivial. Both sides of it are 0. So we're going to consider some kind of open surface A, let's say, which is bounded by a curve C. Right? So curve C forms the boundary of that surface, in other words. And so we're going to take equation 3 of Maxwell's equations, and we're going to dot it into the n hat unit vector, which as usual is a unit vector perpendicular to the surface we're looking at, and then integrate over that surface. Okay, so on the left-hand side we've got the curl of E. We're going to dot that into n hat and integrate over the surface A. Okay. So there's a d sigma for element of surface area. On the right-hand side, pull the minus sign out in front, of course. We've got dB dt. We're going to do the same thing with that, dot it into n hat, and then integrate over our surface. Okay,
Should that be a closed interval? Or no?
no, because it's an open surface,
Yeah, okay.
right? Not a closed surface. Okay, the left-hand side here, we can use Stokes' theorem. Right? Stokes' theorem says if we have an integral like this, that this is equal to the integral of E dot dr around the closed curve C that forms the boundary of the open surface A that we were talking about here. Okay, so this is by Stokes' theorem. And what about the right-hand side? All I'm going to do with the right-hand side is move this time derivative out in front of the integral. Right? We can change the order. We're integrating over an area. We're differentiating with respect to time. Those are sort of two independent operations. They can be done in any order. So this is going to be minus the derivative with respect to time of a b dot n hat d sigma integral, integrating over the surface A. So in other words, then the final result of all of this is the integral of E dot dr around some closed curve C is equal to minus, sometimes you'll see this written as phi sub b, derivative of that with respect to time. This is the magnetic flux which is just shorthand for this integral right here. Okay? So, or to write it out, this is then minus derivative with respect to time of the integral of b dotted into n hat d sigma, integrated over the area whose boundary I'm integrating over here on that line integral on the left-hand side. So that's Faraday's law. That's the integral form of Faraday's law. Okay? So that's the third one of Maxwell's equations. So again, originally it said the curl of E in the differential form was equal to minus dv dt. And now the integral form says that E dot dr integrated around any closed path C is equal to minus the derivative with respect to time of the magnetic flux integral B dot n hat d sigma integrated over the area enclosed inside of the curve that we do the other integral on the left-hand side over. Okay, so that was the third one. We're going to do a similar thing for the fourth one.
So the first one was Gauss's law, the third one was Faraday's. What was the second one?
It's called Gauss's law for magnetism.
Okay.
Okay, and the third one is Faraday's law. And the fourth one that we'll fill in here in a minute is the Ampere-Maxwell law. Okay, so that fourth one, we're going to do a similar manipulation to what we did for the third one. So in other words, we're going to take equation 4 in differential form that I just erased here from the board, or putting it over here, it said that the curl of B was equal to mu naught J plus mu naught epsilon naught dE dt. So we're going to take that equation, we're going to dot both sides of it into the n hat unit vector. So again, we're imagining, first sentence here still applies, imagine an open surface A bounded by some curve C. N hat is a unit normal vector to the surface. So we're going to dot equation 4, dot both sides of it into n hat, and then integrate over that area. Okay, so we've got the curl of B dotted into n hat d sigma integrated over this area A. On the right-hand side, the mu naught can be pulled out in front because it's a constant. So J gets dotted into n hat and integrated over this same area A. And then in the second term, the mu naught and epsilon naught are constants. They can obviously be pulled out in front. And so we've got inside the integral derivative of, I wrote it in terms of E, not D. Derivative of E with respect to T dotted into n hat d sigma and integrated over the area A. On the left-hand side, just like we did over here, we can use Stokes' theorem. This is equal to the integral of B dot dr integrated around the closed path C that forms the boundary of A by Stokes' theorem. On the right-hand side, this integral right here, ignoring the mu naught out in front, well, that looks like a current, right? We were just talking earlier about the fact that the way you go from a current density to a current, you take that current, you dot it into a unit normal vector to the surface, and you integrate over that surface. So this is equal to the incurrent, and maybe I should put a subscript E and C for enclosed. That is a current enclosed inside of, I guess we could say, inside of the curve, right? The current enclosed inside of that curve C, or in other words, the current poking through the area A that I originally was integrating over, right? Imagine that area as you know, sort of some membrane or something like that, and we have current penetrating through that membrane, right? That's the enclosed current. Or another way of thinking about it, imagine the current, or the path C, the closed path that forms the boundary of that area. Maybe think of it almost as if it were a wire loop or something, or a loop of some type. Any current that pokes through that loop is counted as enclosed current, right? And that comes from the result of doing that integral. And for the second term on the right-hand side, I'm going to do the same thing I did for the only term on the right-hand side here. I'm going to just pull the time derivative out in front of the integral. So this is the derivative with respect to time of the integral of E dot n hat d sigma integrated over this area A, or sometimes this is written as this integral is written as the electric flux, phi sub E, right? Flux. You know, the common feature, whenever we use the word flux, it means we're taking a vector field, dotting it into an n hat, and integrating over an area. So this is the electric flux. Similarly, back here, this was the magnetic flux. Similarly, this is the current flux, right? So anyway, putting this all together then, to get the integral form of Stokes' law, on the right-hand side, we have the integral of v dot dr around a loop, a closed path that forms the boundary of some sort of area. This is what we normally call an Amperian loop when we do this integral. And so this is equal to mu naught times the enclosed current passing through that loop, plus mu naught epsilon naught times the integral with respect to time of the electric flux, or in other words, the integral of E dot n hat d sigma, integrated over the area A that is enclosed inside the Amperian loop C we had over here. So this is the integral form of the Ampere-Maxwell law. So the integral forms are the forms that you have seen before, but you've now seen how they're related to the differential forms, which are usually considered to be the more fundamental ones, but they are equivalent, right? These two turn into these two via the divergence theorem, and these two turn into these two via Stokes' theorem. Okay, so let's look at a few special cases. We've only got a few minutes left here, but I think we have time to look at a few cases that you've undoubtedly seen before, but just to remind you of how we use these things. Let's say we have a point charge Q. Let's imagine the positive point charge at the origin. And it's surrounded by vacuum. There's no other material that we need to worry about. Well, you know, the way we usually describe this in introductory physics is that we say, well, you kind of have to know the direction of the electric field. What I'm going to use here is find the electric field set up like this. And of course, we're going to use Gauss's law to do that. The way you often hear this described in introductory physics is that we say you kind of have to know the direction of E before you start. Actually, strictly speaking, that's not true. But it is certainly by far the easiest way of solving this problem. So in this case, we know that the electric field, for example, right, it has some magnitude which is a function of r, which hopefully we're going to find here in a minute, but its direction is the r hat unit vector in spherical coordinates, right? Because it points radially out from the origin, from the charge in all directions. Now, you really don't have to assume that. It is possible, of course, what we're going to choose for our Gaussian surface here is a sphere of radius r. And we want to find the electric field as a function of r. And so if we're at a certain distance, like we're right here at this location, a distance r away from the charge, we want to find the electric field at that point. Our Gaussian surface has to pass through the point at which we want the field, and we want to exploit the symmetry of the problem in a way that I'll clarify in a minute. In other words, our Gaussian surface will be centered on the charge, and it will pass through the point at which we want the field. Now, again, you know, I told you a minute ago, you kind of have to know the direction of the electric field before you start. You really don't, in the sense that if you pick a Gaussian surface of some other shape other than a sphere, you can actually show that the theta and phi components of the electric field are 0. Okay? But usually what we do is, you know, we say, well, okay, we kind of have to know the direction of the field already, namely that it's the radial direction, but you really don't have to. It's just, it just makes the problem a lot easier if you do that. So anyway, Gauss's law, and it's usually easiest to use the integral form when you're actually doing calculations like this. So, so the integral of E dot n hat d sigma integrated over this surface S, this Gaussian surface. Remember the argument we use, we say, okay, n hat is pointing radially outward. That's parallel to E. So their dot product is just the product of the magnitudes. And the magnitude of n hat is, of course, 1, since it is a unit vector. So this is just E integrated, the magnitude of E integrated over the area. And then we make a symmetry argument. We say that, well, because every part of the surface is the same distance from the charge as every other part, we don't expect the electric field to be any stronger or weaker here than here, than here, than here, than anywhere else on the surface. So in other words, as we integrate over this surface, E remains constant. That means we can pull it out in front. And the integral of d sigma is just the entire surface area then. And since this is a sphere of radius r, that entire surface area is 4 pi r squared. And of course, the enclosed charge is just the charge q that we've got in here. That's the only charge located inside our Gaussian surface. So using Gauss's law, the integral that we've evaluated here on the left-hand side is E times 4 pi r squared. On the right-hand side, the enclosed charge with little q, we divide that by epsilon naught. So we can solve this for E as q over 4 pi epsilon naught r squared. Okay? And to make our answer complete, we should put in the direction of E also. by putting an r hat unit vector. Okay? So that's the usual electric field set up by a point charge, or Coulomb's law, as we often call it. Okay? Well, the electric field is also involved in Faraday's law. So let's take a look at what Faraday's law tells us in this example. Okay, so Faraday's law, well, in spherical coordinates, which is obviously the coordinate system we want to use given the symmetry of our problem here. Okay, we've got a point charge at the center. We've already used spherical coordinates in a sense by writing that r hat over there. So in spherical coordinates, the curl, remember we figured this out in chapter 10, it was 1 over r sine theta times the derivative with respect to theta of sine theta times e sub phi minus the derivative with respect to phi of e sub theta. All of that times r hat plus 1 over r sine theta derivative of e sub r with respect to phi minus 1 over r times the derivative with respect to r of r times e sub phi. All of this times theta hat plus 1 over r times the derivative with respect to r of r times e sub theta minus the derivative of e sub r with respect to theta, all times phi hat. Okay, so now that's in spherical coordinates. But in this case, right, the electric field only had an r component. In other words, e sub theta and e sub phi are both 0. So most of these terms are 0, right? This is 0 because of e sub theta being 0, as is this. E sub phi is 0, so that's 0, and that's 0 because of that. And e sub r depends only on r, not on theta, and not on phi. So that means this derivative and this derivative are 0 also. Okay? So the curl of E is 0. We also don't have any, no, I'm sorry, I'm thinking of the wrong one here for a minute. So the curl of E is 0. And as we pointed out before, this means that E is minus the gradient of some scalar potential V. Okay, now, more generally, remember we said that E plus the derivative of a vector potential with respect to time was equal to minus the gradient of a scalar potential. But in this case, there's no magnetic field, and therefore no vector potential, so that term has gone away. Okay? Well, what about the potential then? We should be able to find the potential too. Right? E is minus the gradient of V, and in spherical coordinates, the gradient gradient of V is dV dr times r hat plus 1 over r dV d theta times theta hat plus 1 over r sine theta dV d phi times phi hat. Well, in our case, again, the electric field only has an r component, right? It's E sub r times r hat, and of course this was equal to q over 4 pi epsilon naught r squared times r hat, as we found from Gauss's law. And so given that E is minus the gradient of the potential, that means then that the derivative of the potential V with respect to R, right, that's the R component of the gradient in spherical coordinates. So this must be equal to minus E sub R. In other words, minus q over 4 pi epsilon naught r squared. So integrating with respect to r to get v, we find that v is q over 4 pi epsilon naught r, which is our familiar expression for the potential set up by a point charge. Okay, I was going to do one more example too, but it looks like we're out of time, so I'll leave it for next time. It's not anything you need for any homework or anything like that. And let me also reassure you, I'm not going to ask you on the exam anything specifically related to electricity and magnetism. Okay? I'm not going to give you a problem with charges or anything like that on the exam. I'm only mentioning this stuff to hopefully make the math make more sense to you. Okay? And so I'm hoping that it did this and also maybe reminded you a little bit of the stuff, but I'm not going to ask this on the test. So we did an example of the electric field set up by a point charge, and we kind of analyzed it both in terms of Gauss's law and Faraday's law. The other example, which we'll do next time, we'll consider the magnetic field set up by a long, straight current-carrying wire, simplest magnetic case you can imagine. Analyze it in terms of Gauss's law for magnetism and the Ampere-Maxwell law. Okay?